and if that is what actually can shape our perception. A very, very quick primer on how we study the brain. Okay, we put this big hairdryer on people's head. Okay, it's called an MEG, and what it does is measures brain waves. It's extremely sensitive. All of us have a magnetic field out surrounding our skulls, actually, every one of us, because our brains are electrical. There's currents flowing in our neurons. And when we get enough currents flowing in the same direction, we can actually measure a magnetic field, a very faint magnetic field outside the head. It's a sense we're almost like miniature transmitters. So we can measure that. It's about 1 billion times weaker than the Earth's magnetic field, so we can't exactly bring a compass and try to understand what people are thinking. But by doing this, we can actually try to see inside what's happening. So in this experiment, just play those stimuli, that first one without accents, and ask people to hear it with a beat on the first note or a beat on the second note. And we can just ask, well, how do the brain responses change? And this is an important kind of design because the sound is not changing, like that face bass. The sound is always the same. The perception is different depending on where they hear the beat. So by looking at these two different conditions, looking at the brain's responses, the idea is we can find out which aspects of the brain's response to sound kind of follow along with this internal beat that Steve was talking about, this imagined, ineffable thing. It's not expressed as movement, it's just in there, and it's shaping how we hear things. So, to cut a really long story short, in a first study with those same stimuli, what you see here are curves of the brain response to sound. The blue one, for example, you see a response to the first note. The onset of the note is indicated by these gray lines. So after a note, there's a peak in the response, and after the second note, there's another peak. But what was very interesting is that the peak is larger here in the blue curve. And recall, that's the curve, that's the case where they're hearing the beat on the first note. Okay. And that note's not any louder. They're doing something internally that makes that note more important. Okay, so this is the first sort of sign we found of this internal beat actually influencing how we process sound. Since then, we've gotten a bit more elaborate, and we have a study now where we're looking at rhythms that are syncopated. And in our sort of simple definition of that, it means that actually there's no sound on the beat. Like Steve was saying, the beat is it's felt, but it's not actually expressed in the music. And that's a slightly different situation because before we always had a note on the beat. So we're looking at, well, how does the brain's processing of the note, how is that modified by the beat? Well, what we really want to find is, well, where's the beat coming from, okay? And if we have a sound coming in every time there's a beat, it gets really hard to disentangle where the beat's coming from. So by using syncopated rhythms where the beat and the sound are sort of split apart, we can try to look at that. So I don't have time to go into the details, but we found a number of brain regions where the responses followed the sound in that they really just cared about the sound. They weren't affected at all by where someone was hearing the beat. And these are some expected areas in temporal cortex. This is where auditory cortex is. Something interesting going on up here as well in parietal cortex. But then we also found some areas where the brain's response actually doesn't care about when the sound happens. It only cares about when the beat happens. And you see this kind of curve here. These curves have been aligned on the time of the beat. So actually the sounds are happening all over the place, but these brain areas care about when the beat is happening. And you see motor cortex and premotor cortex. Okay? So, the next step is really to understand, well, how are these areas talking to each other? What's the interaction?
They're not moving.
Yeah, and you're a very important point. They're not moving. Okay, all this I've been talking about the beat. It's in the absence of movement. It's this internal beat that is not sounded and is not acted on that Steve was mentioning. So okay, to sum up, that's a really quick tour about how we think about the beat and what we do with brain science. I would say the beat is important for a bunch of reasons that we mentioned. It gives us a great way to study auditory motor interactions because people can change how they hear the beat. Motor system may affect perception, even when you're not moving. And then maybe we can use this more and more towards understanding and helping people with movement disorders.
I'd like to just interject something really quickly before Anya takes over, and that is, of course, this idea of a beat being heard in multiple ways is actually at the root of a lot of compositional impulses. I mean, when I was a kid, for example, I loved Honky Tonk Woman, and I was trying to understand. And the first time I heard it, I thought the beat was on the second note. And I couldn't figure out how the drummer knew when to come in, how the drummer was to go boosh, ba. And then I realized, no, he's playing it on the first note. Big ba, ba, like that. And so that was an example of the face bass and rhythm. And then Beethoven does it all the time, you know. If you're in a meter of 3, like in the Eroica Symphony, the third one, ee bum bum, bo dee da bee bum bum bum. And pretty soon he'll start accenting every other beat. Bum, bee, pop, bum, tee. So every 2 beats instead of every 3 beats. And for a while, you're swimming because you're thinking, is it in 3? Is it in 2? And you know, someone with a skill level as a composer of Beethoven will reel you out just far enough so that you're really confused, and then he'll snap back. And that moment of being snapped back, and I mean that in the most loving way, you have a kind of revelatory, you know, there's nothing sweeter than knowing where the beat is. You know? It really is. Sorry, I just don't want to throw it out. That's good.
Well, I'm going to just follow up on John before we get back to some music from Steve. So John's talking about human beat perception and our attempts to study that. But one of the deep questions is, again, what kind of brain do you need to feel a beat? Now, Steve mentioned that we're full of rhythms, we're bags of rhythms. I love that terminology. And it's not just true of us. Any mammal would be a bag of rhythms. The monkeys have heartbeats and breathing that's very periodic, and they're experiencing many of the same physiological rhythms, the endocrine system and so forth. And yet we have that intriguing finding where they just find it so hard to do something that we consider so simple, which is feel a beat and move to it. Well, what about other species? Are we unique in this regard? And what kind of brain do you need to do this? Is this something that our brains specially evolved to do, or as John mentioned, did it come along for the ride with some other brain system that evolved? Well, we'll get back to that. So, John, how do I get back to slideshow? Great. All right, well, one of our first entry points into this question was the realization that there's something special about the connection between sound and movement in this whole beat business. I mean, you can get temporal information through multiple modalities. You can get it through sound, you can get it through vision, you can get it through touch. So, are they all equally good at giving you a sense of beat? Well, we studied that by doing an experiment a few years ago where we presented temporal patterns to people as either sounds or as exactly the same timing patterns as flashes of lights. So that your brain is getting precisely the same temporal information. You're just getting it through your ear or through your eye. And you can resolve the individual light flashes, so you can tell that they're individual. So this is what a pattern would sound like if we made it in the form of a sound. And the task was simply to tap to the beat. And so people found this pretty easy, even untrained people. So, and so on. Okay, so people found that very easy. Then we just changed it to a pattern of light. So every time you heard a tone, instead of a tone, you would see a flash. And we asked people to tap to the beat of these things. Well, what happened? Well, people tapped away very happily. And then when you went back and looked at their tapping, there's absolutely no relationship to this practice. So they're just like tapping away at their own preferred tempo. And they're just not able to extract the beat at all. I mean, it wasn't even like they were slightly worse. It was just hopeless. They couldn't get it. So there's something special about this auditory motor link when it comes to beat perception. And again, we talked about how monkeys can't seem to do it, even to a simple metronome. We're not talking about monkeys tapping to these complicated syncopated rhythms. We're talking about a metronome. And this is something a child of 4 or 5 can do without any training, very easily. So, okay, and that's been published in this journal, Neurophysiology. All right, so where is this special connection between hearing and movement coming from in our brains? Well, our hypothesis is that it's coming from something that we do that's very unusual, called vocal learning. Now, vocal learning is just simply the ability to imitate complex sounds. You hear a sound and you can imitate it, and this is something we just do as part of learning a language. It doesn't seem that special to us. Babies in every culture learn to imitate the sounds of their language. Now, this turned out to be very unusual from across the animal kingdom. We're the only primate that can do this. Monkeys don't do it, chimps don't do it, even though they share 98% of our DNA. However, we're not the only vocal learning species. There are other birds and dolphins and some other creatures that can imitate complex sounds, as I'm sure you're all aware, mockingbirds and songbirds and parrots and so forth. And it turns out from some very interesting work being done in comparative neuroanatomy that the circuits that they use, that these birds use to vocally learn, seem to be somewhat similar to the circuits we use to vocally learn. That's a schematic of a parrot brain and a human brain, not exactly the scale. Those red areas are motor areas, and the blue areas are auditory areas, and there's interfaces between them. And it turns out from this comparative neuroanatomy, even though we evolved vocal learning independently from birds, because they're very distantly related to us, we use similar brain kinds of structures. And some of these same structures, it turns out, for imaging research in humans are involved in beat perception. So we led to this idea that maybe this is the foundation for moving to a beat. Maybe you have to have a vocal learning brain to be able to move to a beat. Now, that is a hypothesis that makes some testable predictions. For example, dogs are incredibly intelligent creatures, and they love us. They will do anything to please us. But the point is, they don't have vocal learning brains. They don't learn how to imitate complex sounds. They have some innate barks and growls and stuff like that. So the hypothesis is, if you need a vocal learning brain to move to a beat, you could never train a dog to move to a beat. No matter how smart the dog was, no matter how much time and how good your training methods were, you just could never do it. They don't have the right kind of brain. Just like you could never train a dog to, read a newspaper out loud, no matter how. So, on the other hand, there are animals that are vocal learners, and perhaps they could learn to move to a beat. So that's the other half of the hypothesis. Some animals shouldn't be able to do it, some animals should. Well, we kind of published this as a theoretical paper in 2006, thinking, well, we'll never get to test this idea. And then, about a year later, I got an email from a colleague sending me a link to a YouTube video. And John got it at the same time. And I think we must have watched it on the same day, because we both simultaneously immediately wrote to the owner of the bird, Snowball, who was dropped off at a bird shelter in Indiana. So the video was of him dancing to the Backstreet Boys, a song to the band the Backstreet Boys. And he seemed to be synchronizing to the beat. We were both just amazed. This was the first potentially convincing case. But of course, it's a YouTube video. What's going on? Is there a human off camera? Is he a puppet? You just don't know what's going on. So we wrote to the owner and said, would you collaborate with us on a proper scientific study? This is actually, we have a hypothesis, this is an interesting question. And thankfully she said yes, and she's become a colleague of ours, Irina Schultz, at Bird Lovers Only Rescue Service in Indiana. She's a wonderful person and had a background in science as well. So we just did a simple experiment to test if this was real. We took the song we saw him dancing to on YouTube, we slowed it down, we sped it up with a computer to set like 11 different speeds without changing the pitch. We made sure nobody was dancing off camera, and we filmed Snowball. And then we had those films sent back to us, and we turned off the sound, and we had people who didn't know about the study code the movements of the bird, and then basically to see if they lined up with the musical beats. And bottom line is that they did. And he could adjust to different tempi as well. So he really was sensing the beat of music and moving to it. First demonstration of another species besides us. Now I want to show you a couple of quick videos. These are not YouTube videos, these are from our studies. To give you an example of what we call his synchronized bounce. So when Snowball dances, he just loves to dance, and he'll dance to the whole song. But he synchronizes in sort of periods, which we call bouts, and then he kind of drifts off and dances at his own tempo. He'll come back and synchronize again. We showed statistically that this happens much more often than you'd expect by chance. So he really is feeling it. So this is one of these bouts from a slow tempo, for middle. This is close to the original tempo of the song, a little bit slower. Fastest condition. This is 20% faster than the original song. Now remember, he's never heard these versions of the song before. Okay? So, now this is a really interesting video, because as you'll see, it's too fast for him. And he's struggling. He's trying, but he struggles. But and I should mention, he's not doing this this for a food reward. It's not like he's doing this.